And you see it's going to take like 10 times longer to have this conversation.
Hi everyone, welcome back from the coffee break. So now I'm happy to introduce you to Konstantinos Meichanetzidis, who will give a lecture tomorrow on quantum linguistics. But today he's here also representing one of our sponsors, Quantinuum. And so now he'll talk a bit about what they do there and what are the career opportunities.
Thank you. Can you hear me well?
I think you don't turn it on.
Okay. You can hear me. Thank you very much for the introduction. And yes, I'm Konstantinos. I'm a senior research scientist at Quantinuum. I am based in the Oxford office. And I'm going to give an overview of the activities of the company and the future roadmap and the career opportunities. So, first of all, Quantinuum is a very young company in the sense that it's the result of a merger of Cambridge Quantum Computing, which was a UK, and it still is, a UK-based quantum software company. Started in Cambridge and then grew to London and Oxford. And the other part of the merger was Honeywell Quantum Solutions, who bring the hardware. The hardware specifically is ion traps, and we're going to talk about this in a bit. And now, December 2021, after the merger, we are called Quantinuum. And so we are a global company with presence in the US, UK, a satellite office in Japan, where some scientists and business development people are based, a new office in Germany, in Munich, where the focus is condensed matter and many-body simulations. And soon we will have a satellite office in France as well, in Paris. And it's a big company. It grew very fast, very recently. After the merger, it was around 300 people, and now we are 425 in total, and the scientists are the majority, 350 engineers and scientists, and software developers and technical people in general. Quantum computing. I don't have to say much about it to you, this audience, and so I'll say it very quickly. Quantum computing is about controlling quantum systems, to do quantum information processing, to solve hard problems that are, and when we say hard, we mean hard for classical methods or any other method we know of. Feynman said some time ago that it's a good idea. So now it's a huge industry. It's $1 billion industry. And it's very exciting to be part of it. Now, the era in which we are now, it's called the NISQ era. You probably have heard this acronym. It stands for Noisy Intermediate Scale Quantum. So it's devices that don't have error correction, but the qubits are many enough and good enough that they become interesting. You have heard that Google announced a quantum supremacy experiment. You have heard the controversies. You have heard the follow-up experiments. And we can talk about that later at the lake. I can describe what it's about now in maybe 10 seconds. So what supremacy is about is we say we don't have error correction, we don't have very good error mitigation techniques, and we don't know what program to run to show quantum advantage. So let's run all possible programs, and that's called random circuit sampling. And then we need statistical tests to verify that the thing that runs these programs is actually quantum. And you do this by sampling all the outputs of the device and then checking specific quantities. And these tests have been passed with higher and higher fidelity. The benchmark against them is very smart, very sophisticated classical simulation techniques involving tensor networks and other tricks to simulate the noise, the effect of noise. And so it seems that if you have 60 qubits and above, you are in the regime of quantum advantage, where you need a huge supercomputer to even simulate what's going on, even if that's that thing that is going on is not totally useful, but it's a very specific and important milestone. Here I have a complicated Venn diagram of all the scientific areas that quantum computing can and probably will impact. And they range from the natural sciences to mathematical problems to, of course, where it started from, physics and chemistry. And of course, we are a business, so we care about the financial motivation. And there are many billion-dollar markets that would benefit from having a fully scalable, fault-tolerant quantum computer. From technology markets to chemistry to finance. And so you have a lot of players interested in the industry from many different areas, not just physicists as it used to be in the 90s, for example, or mathematicians that care about factoring. And so we have a quantum readiness program where we think that creating proof of concept pilot programs with industry players is very important, because you get a very good sense of what are the real world problems that people care about. And so we try to see what we can do for these problems with the quantum computers we have today, or the quantum computers we estimate we will have in within the decade. So, as I was saying, we are somewhere here, where there have been experiments on quantum supremacy, and then we go into a regime of trying to predict the future with the technology we have today and what we estimate we will have within the decade. So, to make it specific for our company, we have identified some milestones here. For example, in December we released the first quantum random number generator that generates quantum certified randomness, or quantum enhanced keys. I can talk about this a bit later. And that is called Quantum Origin. And then recently we also released in Quanto a quantum chemistry simulation package. That happened in May 2022. And then in the future, as we go more and more out of the NISQ era and we start having bigger quantum computers, more fault-tolerant quantum computers, we can start attacking the harder problems. And you can see that there is an onset of applications that get unlocked every time you reach one of these eras of technology at the bottom. So these arrows show different areas of research that we do in the company. So I'm going to go over them, and at the end maybe we can have some questions about them, and I can answer them to the best of my knowledge. So as I said, there's many players. So in terms of hardware, there are many approaches to quantum computing. You probably know about this, so let me repeat very fast. It's not just about ion traps that we have in Quantinuum, but another big player is superconducting devices by IBM, for example, or Google. We have photonic approaches like Xanadu or PsiQuantum, and we have also other technologies based on silicon. And every one of these approaches has pros and cons. Right? For example, superconductors are very fast but very noisy. Ion traps are very high fidelity, the highest that we have on the planet, but very, very slow. Photonics have very high loss. You lose basically 40% of your photons or something like this. So there is no one solution fits all. There is no silver bullet so far. So we are all working on all of them at the same time. Here I'm showing that quantum volume has been increasing linearly. I know that people have defined quantum volume in a log scale, and to be honest, I don't like this personally, because they try to make a contrast with Moore's law. So if you want to understand what quantum volume is, you take log 2 of it, and that basically tells you morally that that's the size of a square circuit you can run without errors, up to some acceptable error of fidelity. So when we say quantum volume 4096, we mean that machine can simulate 12 qubits very, very well. That's what it means. And when we say it grows linearly, we mean that every 1 year we can add another qubit and we don't introduce noise. That's what this graph means. So we have been doubling our quantum volume, x timesing our quantum volume every year. And our engineers, they believe they can keep this going for the next years. And this is our hardware roadmap. So now, how it works is every ion is trapped in an electrostatic well, and then they're shuttled around in this corridor, like literally moved around by tuning the electrostatic potentials like wizards. And then you fuse them in the same potential if you want to get them entangled in a logic gate. You shine laser at them, and then they get entangled, and then you unfuse the wells. And there is a hard optimization problem to solve there, which is in general NP hard. It's called the traffic jam problem. As you can imagine, these things, they need to be regulated. But then in the future, when we move to 2D architectures, we think we can do more sophisticated shuttling. And they actually, there are videos online of the Honeywell Quantum Solutions platform where you can actually see videos of these cold atoms being shuttled around corners, which is, I mean, it sounds cute, but it's really, really hard to do. So it's very important that this can even be done. So this is not just speculation, it's not just wishful thinking, this is going to happen. These architectures are possible. What's difficult is to go 3D, so that's another conversation. But until 2030, I think we can manage with 2D architectures. And this is the full stack. So hardware is at the bottom, and then we have a full stack which is built on software and applications. And I'm going to go through over these applications and talk about them one by one in a bit more detail. So here what we have is the software is sitting above the hardware. Of course, the hardware can be any hardware. I want to emphasize this. So of course we own the ion trap machines powered by Honeywell, but the software that we are building compiles into any platform, almost any platform, and so the circuits and the programs that you run in the software development kit, for example, ticket, they are agnostic to the hardware, right? Of course, you have to do this. Like you want Windows to run on every laptop, right? It doesn't matter if it's Lenovo or whatever. We want the same thing to happen in quantum. And so at the top, we have applications that are built on top of this software. And they range over chemistry, cyber, AI. And so let's see what they are. So let me do some advertising and celebrating here some achievements. So I talked about quantum volume. A very important thing that the hardware team has achieved was to actually run on error correcting code and correct errors in real time, not just error mitigation. There's been new algorithms for combinatorial optimization from the QML team. I'm going to talk about that. We have a very high spam fidelity. There is a record in that actually from the hardware team again. Spam means state preparation and measurement. So you want these things to be exact as possible, so that you don't care about them and then you actually care about the circuit. Ticket is our very good compiler. It beats most of the benchmarks in the majority of family of circuits that people care about. So that is about optimizing circuits, right? So for example, on a superconducting circuit or ion trap circuit, the single qubit gates are much, much less noisy than the 2 qubit gates. And so given a circuit, you want to apply some rewrite sequences to optimize it and get it to be, for example, with as few CNOT depth as possible, as few CNOTs as possible, minimize the CNOT depth. We have launched Lambec, which is something I'm going to talk about tomorrow also in my lectures. Lambec is a toolkit that allows you to do quantum computational linguistics and do NLP tasks on NISQ devices. It's a research tool. And let's see, I talked about quantum origin, and in Quanto also I talked about it. So let's see what they are. So hardware, I guess I talked about already. So this is more specifically the numbers for the fidelities as measured by the standard benchmarks that you would use, and you can see they increase every year. Not just the fidelities increase, but also the number of qubits, right? So it really makes a difference if you go from 10 to 20 qubits. It really does. And they're not just 20 worse qubits. I mean, this is really important. It's like when I run circuits with these things, it's like you're running a an exact simulation on a laptop. They're really, really exact. The only drawback for now is that they're kind of slow, so you cannot do variational things. But still, they're very, very impressive. Now, here's, for example, a paper published by our partners, JP Morgan, led by Marco Pistoia, where exactly what I said was done there. They check against noiseless simulation an algorithm that does combinatorial optimization using this device, the new device with 20 qubits, and they get fidelity as high as the clean clean classical simulation of the quantum circuit, which is very, very, very impressive. Now I'm going to switch to cyber and talk about what Origin is. Also, Cameron is here, so Cameron Foreman is here, so any questions go to him for this because he's in that team. Now the idea here is that there's many ways to attack a cryptographic protocol. And the one we focus on is about the key generation itself. So the idea is there that if you use a low entropy source to generate your cryptographic keys, then someone could take advantage of that and try to predict them. And if they succeed, then they can hack you. So the idea of quantum origin is to use an entropy source that comes from sampling a quantum computer. And there are statistical bell tests that you can that you have to pass so that you certify your entropy. The only loophole is that you have to trust that that the quantum computer is not malicious, right? That's all you have to trust. After that, it's all certifiable that the keys are truly random in the sense that you pass all the statistical sense. Let's not get philosophical about like randomness in the universe. And then here's a slide of partners that are actually using this. This is a product that is available today. Quantum Origin is something you can buy today. It even made it to a pure VPN protocol, which is very cool. And now let me talk about QML a bit. So QML is about, I mean, it's a very fancy word. You put so many buzzwords together and people get excited, but what it is really is, you know how you can train neural networks to do stuff? Well, here you swap out a neural network with a quantum circuit, and the parameters might be, the gates might have control parameters, like you have control RZ of theta, and that theta is the analog of a weight in a neural network, right? Weights and biases in neural networks, parameters of gates in a gate-based quantum computation, right? That's the gray box. Then you can measure and stick it on a neural network if you want, or let the Born rule be your nonlinearity, right? These are also called Born machines in some literature, which I think is a good name because it really tells you what it does. I don't like it, for example, when they're called quantum neural networks, because then you get confused, like what is a quantum neuron, right? So the idea here is that you have to use a classical computer to optimize the parameters of the quantum circuit. And the quantum circuit is queried to get the cost function out for some optimization problem or some learning problem or whatever. So you query the quantum computer, you get the cost function out, the classical optimizer updates it, and then you loop around until convergence, and that's quantum machine learning. All right? And it has many applications. So the applications are from inference to capturing correlations of a complicated data set, and anomaly detection, things like that. I have references here for anyone who wants to go deeper. Now, let me give you some intuition for why you want to do this even. The idea is that there are that these quantum circuits, they generate probability distributions, right? In the sense that you're making a wave function on many qubits. To simulate this quantum, classically it's hard if the thing is very big, right? In terms of width and depth. And so sampling from it classically is hard. So if you can use it for something and it turns out to be useful for a task, and there is no other classical learning approach that, if you compare fairly against, does better, then you can say that because this is very expressive and it can capture more correlations than classically, then you really need a quantum computer to implement it, to run it, or even train it. And so the idea is that you have a solution, you're looking for a problem, right? The solution is quantum computing can create probability distributions for you that are hard to sample from classically. They're just more expressive models. Then if you find a use case where these things are useful, automatically you have a quantum advantage. So our team in London, they do this. They look for corner cases of machine learning where these expressive models might give you an advantage. And a similar thing you can do with combinatorial optimization. There you don't have a generalization problem, you don't have to learn anything. All you have to do is use the quantum computer as an ansatz for preparing either a wave function or a probability distribution over some data, and then you have to train your ansatz, as you do when you're a physicist. And you, for example, have a tensor network representation for a ground state. Here you don't use a tensor network simulated on your laptop or supercomputer, you have a quantum computer directly. So a highlight was filter VQE, which is a method to make parameterized quantum circuits converge faster, right? So this is a very nice paper. I'm putting it there for you to read it. And if you compare this method against the other standard variational quantum algorithms, the standard VQE or quantum approximate optimization algorithm, QOA, then you see a speed up in convergence for combinatorial optimization. So when I say combinatorial optimization, what you do is your Hamiltonian encodes a classical optimization problem. So it's all diagonal, right? It's hard because you have exponentially large solution space. That's where the hardness comes from. And then you use a quantum ansatz to optimize a classical Hamiltonian, and then you might have a benefit because again, as I said before, these models can be more expressive in terms of the correlations that they capture. So applications of this, the London team has applied it to scheduling problems, like scheduling a factory or scheduling railroad traffic networks. Right, and quantum chemistry, I'm going to switch to quantum chemistry and Quanto. In Quanto is the package I talked about for simulating chemical systems. Now, what is the goal of quantum chemistry? It's the standard thing I said in the beginning that started the whole field even, if you believe the anecdotes by how the field started, where Feynman said, let's use them for simulating quantum systems. Then the idea is that if you want exact chemical accuracy, if you want a chemical accuracy, you should use a quantum computer. That's the idea. These are collaborations we have done. The quantum chemistry team, which is based in Cambridge. These are collaborations they have done, published in these preprints. I'm going to very briefly talk about the first one, which has to do with carbon capture. So there is a problem of using metal organic frameworks for carbon capture, and you want to simulate how each one of these captures carbon and retains it. And while you don't want to do this in the lab and waste a lot of materials, you want to try to simulate it and predict how it would do in the lab, and then pick the best material and actually go in the lab and check it out in real life. So what they do is they focus on the part of the molecule that interacts with carbon dioxide, and they partition the molecule in a smart way so that the rest of the molecule is treated with classical approaches like DFT or more sophisticated classical approaches, but then the molecule environment interaction is treated quantumly. And then it's simulated with a variational quantum algorithm, doing a VQE approach, which basically says, I'm going to optimize an ansatz like I had before with variational parameters, and then try to find where the energy minimum is, like where exactly is the ground state energy of this thing interacting, the molecule that attaches with the molecule that you want to absorb the thing that attaches. And basically you want to see where exactly they go and sit, right? And then now let me switch to more software. So software, the software development kit that I mentioned at the beginning of the talk is called Ticket. The Python package that that you can install, you just do pip install PyTicket, was made open source recently, which was a big decision because we wanted to have everyone in the community contribute. And so the main point of Ticket is that it's totally agnostic to any backend and any front end. So for example, any ticket circuit that you write in our language, you can translate back and forth into any other software development language from other providers like IBM or Google. And then you do the thing I said before, you optimize your circuit, it's done automatically according to the backend. And then what you do is you try to apply it to one of these applications that I talked about before, right? So its point is to make your life easy to write quantum circuits without thinking too much. I mean, that's the goal of a nice programming language, right? You want as many people to be able to write a quantum circuit down and describe a pipeline without getting too fiddly about it. And these are papers that have been published about it, about how we solve the routing problem. You know, routing is, you know, you have an architecture. So for example, maybe a superconducting chip says this qubit and this qubit are this far apart in a graph. But my circuit says they should interact. So what do? Just do a bunch of swaps and then swap back? Sure, but then this will increase the depth. So what's the optimal way to do this? What's the optimal way to map a circuit or compile it down to a specific chip with a specific topology? So that's what Ticket, one of the problems that Ticket solves. Now, another application I'm going to jump to very fast is finance. Obviously, everyone cares about finance for obvious reasons. Don't have to explain this. So, what are the problems in finance? Usually, they have a portfolio. They want to optimize how do you allocate, investments into different stocks or assets. It's called portfolio optimization. It's another combinatorial optimization problem. Or you want to do derivative pricing, which basically, or whatever else you want to estimate or predict. What it amounts to is getting expectation values of functions, analytical functions of random variables. And since a quantum computer is a sampler that allows you to sample from trigonometric functions, as you can see in that paper over there, you can use it to Monte Carlo sample integrals or expectation values, either a single point or many body correlators that then are translated to higher order moments in distributions. But then the idea is you get a quadratic speedup, and then you have to worry about resource estimations, because someone working in finance, they don't care about, I mean, to be honest, they don't care about quantum computing so much as the physicists or the chemists care about. But they don't have a research mindset. What they care about is, can I make money today, right? So you really want to do your research estimation very well to have a very good estimate of how soon you can have this quantum speedup. So you really have to estimate everything, like down to the gate. But of course, I'm exaggerating a bit. There are legitimate pure research teams in many banks, for example, JP Morgan, like I showed before, or Goldman Sachs. And they do this type of research, of estimating expectation values and looking for speedups, or combinatorial optimization, like I showed before, the JP Morgan example. And of course, they also try to use machine learning. As you do use classical machine learning, you try to use quantum machine learning to predict behaviors or, again, do optimization problems. That picture over there is called a GAN, a generative adversarial network, where you have two networks and one generates data and the other one discriminates them, and they both converge to be very good at it. So then you take the generator and see what it predicts for you. And so the whole idea here is that if you do it quantumly, you get some sort of advantage, again, with the same reasoning, where if a quantum circuit generates a probability distribution, which is hard to sample from classically, and if it's useful, then you have an advantage, right? It's the same story, just different architectures. And you try to see where and how they're useful. And now I'm going to end with the team I belong to, which is the Oxford team. We have our own logos and everything. And we do the longest horizon type of research. So we mainly focus on the compositional approach to any complex system. So for example, like John Selby said in his lectures, we put on the process theory hat, and then we approach complex problems. So specifically, among all the things we do, let me mention the topic of my lectures tomorrow, which is quantum NLP or quantum linguistics. And for this, we build a package, a Python package, which you can also pip install and play around with. The idea is, in very quickly, because you'll hear about it tomorrow, is that you have syntactic structures that whose mathematics is compatible with process theories. One of these process theories is quantum theory. So the mathematics allows you to map one structure to another structure. And then you try to use it for something. And so if the math allows it, you're allowed to create models that have the structure of the problem hard-coded in your model, right? So that is analogous to how, if you're doing chemistry and you have a Hamiltonian which has symmetries or a specific structure, you put it in your ansatz, right? Because you kill a bit of your parameter space, and you can make your ansatz more specific to the problem, because there is no free lunch. You cannot have one problem that works as well for everything. And so that's what we do here. We take a physicist approach to linguistics, and using these syntax-aware ansatz, we can do quantum machine learning style tasks or NLP tasks that the simplest of which would be classifying sentences into classes, right? So you can have a data set that has sentences and they have binary labels on them, like if it's movie reviews, you say good, bad, right? And then the model has to predict. So every sentence is a circuit, it's run, you get a label out, and then you optimize the parameters such that it learns. And you give the new sentence, and you run the circuit, and the circuit tells you it was a good or bad movie review. So it has learned something. And these are runs that we've done on IBM Q last year, and runs on Honeywell power devices, now I should say Quantinuum devices. But the idea is that you can use Lambec, the software package, to just design whatever pipeline you like, right? So I'll talk about it tomorrow. The idea is you can get syntactic structures, get quantum circuits that look like them, and then do whatever you like with them. Right, so I'm going to end with, join us if you want. I hope this was a comprehensive overview. We have positions for all kinds of technical folk, like from engineers to software developers to all kinds of scientists, from maths to computer science to physics. We're a very diverse company. So yeah, check it out.